Hello guys, I am Ali Jawad and welcome to my YouTube channel. In today's video, we will start with chapter number 22 of Physics Syllabus 5054 for Cambridge students. Before proceeding with this chapter, it is recommended to go through the videos of chapter number 17, that is magnetism, because the title of chapter number 22 is Electromagnetism, and it is in continuation of the concepts which has been discussed in the videos of chapter number 17. So as the word suggests, electromagnetism deals with the study of magnetism and electricity and the relation between them, that how electric current can be used to produce magnets and how magnets can be used to produce electric current. So let us get into it. Our first topic in today's lesson is Fleming's left-hand rule. Fleming's left-hand rule is really important because it gives us the direction of magnetic field, current and force. It gives the relative direction, means whenever you will change the direction of any one of the components, the direction of the rest of the components will also get changed. What does it say? It says that the index finger of the left hand determines the direction of magnetic field. So we will always use this index finger to point in the direction of magnetic field, while the middle finger is used to give the direction of electric current through a conductor, and the thumbs gives the direction of force which will be experienced by the conductor. So for instance, in the diagram shown to you on a screen, the force is experienced by this copper wires in the upward direction, while the index finger is giving the direction of magnetic field, that is from north pole of this magnet to the south pole of this magnet. The current is incoming from this direction, so the middle finger is pointing to the direction of current, and this gives the direction of force. Now if any one of the direction may get changes, the force experienced by this copper wire will also get changed. So how to practically perform this experiment to verify? Let us see this. We can arrange the apparatus such that the copper conductor is being suspended over here with the help of these two wires, and the wires are connected with the terminals of the battery over here. So when the current starts to pass, the current is moving from this terminal and passing through the conductor and leaving the wire or leaving the conductor from this end. So the direction of current is this, while the direction of magnetic field is from north to south. So if you will orient your fingers of the left hand, the index finger is from north to south, the middle finger is giving the direction of current which is moving away from you, then the thumb will obviously give the direction of force. Now notice that in my camera you are observing the opposite direction is drawn on the screen because of the flipping effect of the camera. So this will be the direction of force experienced by this. Similarly, if the direction of magnetic field is from north to south and the current is moving like this, so now orient your fingers again of the left hand, the magnetic field is downward from north to south, while the current is into the screen like this. So you will get to know that the direction of force will be leftward. Now let us try to experience this with the help of virtual experiment. Here we have got the apparatus, and first of all let us try to understand what this actually is showing to us. As you can see, there is a support at the top from which we have connected a spring, and this spring is helpful in suspending this wire. Now note that this wire is suspended between the magnetic field. The magnetic field is being provided with this north and south pole respectively, and the battery is connected to this over here. Now observe the X, Y, and Z axis drawn with the help of arrows in this animation. So here we have got Y axis, here we got X axis, and here we got Z axis. There are triggers given at the bottom of the screen from where we can increase the magnetic field and the current. So I'm checking this current flow, and the current flow X means the current flow in X direction. So when I increases this value, as you can see, the electron has started to move in the X direction, means from the origin towards the X inside the conductor. So you can observe the motion of these electrons. Now if I may go in the opposite direction, so the electron will start to move in the opposite direction. It means reversing the direction of current. Let it be 2.5 for instance. Now notice that the conductor suspended with the help of a spring is not experiencing any force, and it is not moving here and there. However, now I will apply this magnetic field in the Y direction. B is representing the magnetic field. So when I will switch this on, you will see the lines of magnetic field from north to south. See this, the yellow arrows. I am switching it off, so the magnetic field disappears. As I switched it on and increasing the magnetic field from 0 to, let's say, 1, now notice that the wire has started to move in the upward direction. And why it has started to move in the upward direction? Because the current is out of the screen and the magnetic field is pointing like this. So we will use the index finger to give the direction of magnetic field. The magnetic field is like this. Current is moving away from you, means outside the screen. So the thumb will give you the direction of force, and it is upward. So the wire is moving upward. Now notice that when I will switch the magnetic field, what will happen? If I may reverse the direction of magnetic field and switching the north and south pole, so now use your left hand again. This is giving the direction of magnetic field. This is giving the direction of current. So this is how the direction of magnetic field is on the screen. Okay, and you are observing the opposite thing in the camera because of reflection. So the thumb will give you the direction of force. This is the direction of magnetic field. This is the direction of current, and downward will be the direction of force. So let us play this and observe. As you can see, there is a green arrow with a downward force causing the wire to extend in the downward direction. Now I am again making the magnetic field equals to 0. The wire is again moving upward because of the spring we have connected with the support. Now let us try to reverse the direction of current. Now as you can see from the top, the direction of current is opposite. and let us provide magnetic field to this. So the magnetic field is represented with the index finger. This middle finger represent the current. So the thumb will represent the force experienced by the wire. The wire has moved actually downward. Why it is moving upward? Because the spring is trying to return it back to the equilibrium position. So we have observed the effect of reversing the direction of current and reversing the direction of magnetic field. So the angles between these remain same, means this finger represents the magnetic field, this represents the current, and this represents the force. When the direction of magnetic field changes, or when the direction of current changes and it gets reversed away from you or towards you, the direction of force with the thumb also gets changes. Let us try to watch it in real life experiment. This is a video taken from James Dan, a YouTube channel, but it is helpful in understanding the phenomena, so I have made it a part of my lesson. So let us see what he is doing.
So I have here a large magnet, South Pole, North Pole, so the field is pointing up. And then I have a big copper tube, which is connected to the wires here and there. When I connect these here, electricity will flow through this guy, through the red, through the copper tube, and then up through ground, and then back home. So we'll have electricity flowing this way, magnetic field pointing up. We expect a force inward. And sure enough, we get an inward force. Now, if I reverse the direction of the current, we expect an outward force. Get this guy out of the way. And there you see it, floating there. Because now that I've reversed the direction of the current is flowing this way, magnetic field is pointing up, we expect an outward force. And that's what you say. Right-hand rule, simplified.
So today we have learned about the Fleming's left-hand rule and how it is helpful in predicting the relative direction of magnetic field, current, and force. And we have also seen that whenever a wire or a conductor carrying current is placed in a magnetic field, so when current and magnetic field impacts together, they produces a force. But why they produces a force? As we have seen in chapter number 17, with the right hand rule, that whenever the current is passing in a wire, the curl of the fingers give the direction of magnetic field, while the thumb gives the direction of current. So whenever the current is passed in a conductor, a magnetic field is generated around it, which can be given by the right hand rule. So what happens when we place a conductor carrying current in a bar magnetic field? Let us see. Now then there will be two magnetic fields together. The one magnetic field is from north to south, which is because of this bar magnet. And the second magnetic field is of wire, because if it is carrying the current, then the direction of curl of the right hand fingers will give the direction of magnetic field. So now notice that the direction of magnetic field of a bar magnet is same as the direction of magnetic field because of current in the wire, at least in the downward section, while in the upward section they are opposite and cancelling the effect of one another. So when they will cancel the effect of one another, the magnetic fields in the upper region may get cancelled and the lower magnetic field will be high enough to push this wire in the upward direction. So the interaction of these two magnetic fields is causing the wire to move in the upward direction or the downward direction respectively. So one magnetic field is of the bar magnet and the other magnetic field is of the wire itself. This is causing the current carrying conductor to move here and there when it is placed in another magnetic field, as we have seen in the virtual experiment in the video. I hope that you have liked your lessons for today. Don't forget to subscribe our channel to watch the latest videos on the same topic. Thank you for watching.